Okay, so now we're going to take a look at occurrences of variables. So when we have two occurrences of variables, and just in general, we're going to review like terms really quick, because that's a very big piece of the mathematics as we move forward, especially as we're moving into algebra. We need to understand what like terms mean. So we'll go over that first, and then we're going to kind of come down here, and I'm going to show you how to visualize with algebra tiles. So like terms, these are all terms in an expression that represent numbers. Some are constant and some are being multiplied. Numbers that are alike have the same operation and can be combined. How can we group these items down below? So just kind of practice. So I have these little symbols. We can see it's an apple, a grape, an apple, a grape, and a watermelon. So you can already hear me kind of grouping them. I gave them names, didn't I? We have apples, we have grapes, we have watermelon. So I can group them by type of fruit. That's a very simple way for me to kind of separate them out in my head. They're different types of fruit. So this is the same for variables. Each letter represents a different value, or you could think of fruit. They represent a different fruit. So constants are numbers that are not being multiplied, such as 3 or 57. So those are just numbers. I know it's 3, I know it's 57. There's not a multiplication, there's not a division with it. It's just a number by itself. A variable must be the same letter. Different letters represent different numbers. So if I have an x and a y in the same expression or equation, they mean different numbers. So they represent something different. But if I have x and x, they represent the same in that same equation. From equation to equation, they do not always represent the same number. So it's within the same expression or equation. Also, the variables must have the same exponent. This is because exponents represent repeated multiplication. I don't know if I actually wrote that off to the side here. But what I mean by that is, I said if I have x and x, those represent the same number, and I can actually combine those. I can add them together because they're the same. But if I have x and x squared, those are no longer the same, because x is not being multiplied, but x squared is. A square means I'm multiplying it by itself. It means x times x. So it's no longer the same operation anymore. Now I'm multiplying it by itself, and I wasn't multiplying the first x by itself. It's just x. So I know that's kind of a lot out loud. All right, so now we're going to replace the items above with variables and combine like terms. So these items up here, so instead of apple, grape, watermelon, I'm just going to give them variables. And you can use any symbol you would like. We very often use letters as variables. So it's pretty common to see something along these lines, like A for apple, G for grape, W for watermelon. But I could have used the @ symbol, or a question mark, or anything like that. I've actually used question marks in class to prove that point. It's just a placeholder. And you don't have to use letters, but as far as Alex goes, that's what it's not going to accept any symbols or pictures. You're going to have to use variables, letters for variables on Alex. But when you're writing them out in your notebooks or on your notes pages here, you can actually use any symbol you would like as a placeholder there, as long as you're consistent. Once you choose A for apple, you need to make sure that you leave it that way for that problem, that equation. Okay? Or if I did like an @ symbol, or maybe I want to use the picture of the apple, that's fine. That's perfectly fine. It's just a placeholder. So now I'm going to combine. So what that means is I'm just going to look and say, well, how many A's do I have? How many apples? Well, I had 3 apples, and I had 2 grapes, and I only had 1 watermelon. So if I don't see a number in front of a variable, it means it's 1. So I had 3 apples, 2 grapes, and 1 watermelon. So this is a very simple idea of just combining like terms. All right, so now we're going to use algebra tiles to visualize these two problems here. And with this one, it looks something like what we've been doing for the last couple weeks, with the exception of now I have 2 occurrences of the variable. So before it would have been something, like 8 equals 5w plus 3 without that extra w there, right? I'm kind of blocking with my mouse. But now we have 5w plus 3w. So now if I use my little algebra tiles, and we should have these available for you in the center, I truly hope so. Kind of might depend from center to center, but we should have something along these lines. But they are very easy to draw also. So if we look at this, I have 1, 1 all the way over here. And if you count them, I have 8. So what I was focusing on was this 8. I should have highlighted that green so you could see that a little easier. And then I have 5 W's. And then I have 3 W's. So here's the visualization of this problem. Can we combine the W's? Well, why not? They're all just W. I have 5 of them here. I have 3 of them here. Well, how many do I have total? I have 8 total. Yes, we can. That was a Bob the Builder reference there. So it was about my question that I said, can we combine the W's? Yes, we can. So, silly little Bob the Builder joke there. But yes, we can combine those W's. So now I have 8 ones over here, and I have 8 W's over here. And basically what I want to know when I'm using visual representation like this is how many ones go with each W. So if I'm looking at this, I would have 8 equals 8 W. So that's the algebraic view. Here's the visual view. And I can group 1 to 1 W. So it's a 1 to 1. There's 8 ones, there's 8 W's, so each one gets a W. So, and the algebraic view of that is I would just divide by 8 on both sides. 8 divided by 8 is 1, same thing on this side, so I just have W. Remember there's a 1 in front of there, but we don't have to put it. So W equals 1. So again, this is just a way of visualizing. Alright, so for the next one, I have 13W equals 7W plus 12. So now I'm going to show the 13 W's. So here we go. Here's 13 W's equals, and now I have 7 W's on this side. So there's 7 more W's. And then I have plus 12. So here's my 12 ones. Yes, we can. All right, there's my silly Bob the Builder again. So can we bring the W's all to the left side? Yes, we can. I think I need to delay that one a little bit for the yes, we can part. It goes off a little too quick. I want to bring all the W's together. So the way I'm going to do that is we can eliminate 1 W from the left for 1 W on the right. So because they're both positive, so I can just say, well, I'm just going to take 1 away from each side. That's our subtraction property. So I can go 1 to 1, 1 to 1, and I can keep going until I kind of run out of matches. So you can kind of see I've matched them, and I was trying to color code so you could see as it's happening. And what I want to know is how many am I left with here? 1, 2, 3, 4, 5, 6. So I'm left with 6. So if I look at this algebraically, 13W minus 7W, that's exactly what I'm doing with crossing off. I'm subtracting them away from both sides. Okay, so I'm subtracting it away, and I'm left with my 6W, which we saw visually, equals 12. So now 6W equals 12. So now I just want to know, if I group them, how many ones go with each W. This time it's not a 1 to 1 because I have 6 W's and I have 12 ones. So this time I'm going to have to group 2 ones for every 1 W in order to get 6 groups over here. So again, I can see this algebraically by dividing by 6 because I want to undo that multiplication. So W equals 2. All right, so this was, you do not have to use algebra tiles. This was just a demonstration of how to use algebra tiles. But it can be very helpful to visualize. As we get into bigger numbers, it can be a little bit difficult to continue to use algebra tiles because it gets to be a little overwhelming to see that much visual mathematics. So the algebraic method definitely comes in handy. And as you understand what's happening visually, you won't need to see it quite as much. You'll be able to use this method because you'll be able to visualize it kind of more in your head a little bit. All right, so let's go ahead and practice a couple of these. So with these ones, my question down here is, would you choose to use algebra tiles or the algebraic method? So if we're looking at this one, 63 equals 14u minus 7u. With this one, if I were asked that question, I would use the algebraic method, specifically because of this number 63. That is a lot of algebra tiles to either have to draw or have to count out. That's going to take me a while. And then what if I accidentally forget, or not forget, but kind of mess up on my counting or my drawing, and I don't quite have 63. So that's definitely a reason why I would probably go with the algebraic method on this one, because we're getting into those kind of bigger numbers, which is, you know, exactly what I'm talking about down here. Algebra tiles would be very tedious and a little confusing because of the large numbers. So I'm going to use the algebraic method here. So I'm going to combine these ones so we can kind of picture it in our head. Hopefully we have 14 u's, and then I have 7u, and I'm subtracting 14 and 7. So I have 7 left. So I had 14 u's and I took 7 of them away. So I have 7u left. And the 63 is still on the left side there. I haven't done anything with the left side of the equation. So 63 equals 7u. So now I just need to undo this multiplication by dividing on both sides. 63 divided by 7 is 9. So 9 equals u. All right, same thing on this one. I would probably not use the algebra tiles because of 45. That's just another very large number that's going to be tedious and a little confusing to look at once we get all those algebra tiles out there. So with this one, I want to bring the variables onto one side of the equation. So if they're on the same side, you combine, you either add or subtract. If they're on opposite sides of the equal sign, then I need to bring them together by doing my opposite operation. So I can see I'm subtracting 6y, so I'm going to add 6y to both sides because I want to take it from this right side and I want to bring it over to the left side. So 3 plus 6 is 9, and I bring the y with it, equals 45. That comes down as well. But negative 6 plus 6, that cancels out. That's no longer there, because any number minus itself is 0, even if it has a variable. It was a full 6y minus 6y. All right, so you can already see, kind of clicked a little too early there. We want to undo that multiplication, that 9 times y, so I'm going to divide by 9 on both sides, and y equals 5. All right. So that was dealing with 2 occurrences of the variable and reviewing like terms. So I hope that helped, and I will see you in the next video.